Okay, Mr. Hunt here doing the Unit 4 review. This is just extra practice, extra problems and prep to get ready for the Unit 4 quiz and test. So let's jump in. Number 1, so these are all derivatives, or dy, dx for the problems. So the first one, it's an exponential equation. It's a number to the x power of this form, a to the x. So it's not just x, though, it's something else. So the derivative of a to the u being something else, is a to the u times u prime. So here, it's 7 to the log 2x, log base 2 of x. You just write what it is, that's this part. Then I got to do the derivative of this up here. I forgot something. A to the u times u prime times natural log of the base a. So that's where you can follow, I have the answer key for this on Canvas as well. So natural log of 7, that's the base. Then it's times u prime. I could have done this one unboxing, that one, or this one in either order. So then times the derivative log base 2 of x, and log derivatives of this 1 over x natural log a, where a is 2. So that's it, nothing to simplify there. Number 2 is product rule. Cosine x times x squared plus 1. Yeah. Y prime equals f cosine x. G prime is 2x plus g, and then f prime is negative sine x. The only thing I did to simplify, if you look at my answer key, is I put the negative sine x in front and the 2x in front. Kind of optional. Number 3, so notice the difference between 3 and 4. All right, big difference between 3 and 4. Yeah, I'll put them side by side here. Secant x. 4. So 3 is one term, just chain rule. 4 is product rule. So chain rule, this one's product. So the derivative here, it's just, I do the outside derivative. So natural log, that's 1 over, then I keep, it's normally x, but it's not x this time, it's secant x. So it's 1 over, then I put in what my u is, secant x, times u prime, so the derivative of the inside, u prime or g prime, secant x tangent x. Right there. I'm boxing that, I don't know why, because these cancel, so here's what I should box, tangent x. So that's the final answer, since those canceled. All right, and on 4, it's product rule, so I'm going to age. So it's going to be f natural log x, g prime is secant tangent, plus g secant times f prime 1 over x. The only thing I did, you can see my answer key, I combined this to secant x over x. That was it. 5, quotient rule. So f prime or y prime dy dx, low, d high, 0, but then secant squared x, minus high, 1 plus tangent x, d low is negative sine x, all over low squared, cosine x squared. Again, not much to simplify. You could simplify this negative and this negative as positive. That's pretty much the only thing to do. 6 is a product rule. There's two functions there. So I do f, g prime is cosine, that's an s, plus g sine times derivative of the first is e to the x. So that's it. I think on mine I also wrote, you could factor out an e to the x if you want. 7 is a power rule. Oh, I'm writing y, it's f, that's fine. So cosine 5x to the 4. So it starts off as a power rule first, with chain rule involved. So I got to bring down the 4, keep the g, keep the inside. So that g stays the same. Subtract 1, power rule. Okay, then I'm doing the derivative of cosine of 5x, which is negative sine, keep the g, then do the derivative of 5x, which is 5. So that was a double chain rule 1. And then the only thing I did to simplify is there's a negative and a negative, which becomes positive, and the 4 and the 5 make 20. Oh, and then optional, what order you write them in. I wrote this one first, the sine 5x, and then cosine 5x cubed. Okay, number 8 is implicit differentiation. So we do d dx to every term. So the first one, the 3xy, I got to do product rule. F 3x times g prime dy dx plus the g is y times the derivative of 3x, which is 3. Then I have negative 2y dy dx, that's the derivative of y squared, and then 4x on the right side. And then there's two terms with dy dx in them. So I'm combining a couple steps here. I'm factoring out from those the 3x minus 2y. This one, I'm subtracting to the other side. And then I'm going to divide by the 3x minus 2y. Okay. Again, if you get if you get the negative version of every term, that's also equivalent. Number 9 is second derivative. Let's see, A, B, C. So for A, if you want, you could solve a little bit first. I just did implicit differentiation, so I did d dx right to start. And got 2y dy dx, 0 for the 1. And then here, you can do quotient rule, but I brought it up as x to the negative 1 power. And so then I did power rule and got 2x to the negative 2. So then dy dx, I changed this, so it's 2 over x squared. Then I have to divide both sides by 2y. And so what happens, the 2y is down there. So that cancels out, so it's just going to be 1 over x squared y. Okay, then second derivative quotient. Low d high minus high. Okay, now this is interesting. Then d low, we have to do product rule. This might be the first time we've seen product rule inside a quotient rule. So I have to do first, second derivative is dy dx, plus the second is y, first derivative 2x, all over the low squared. And that goes away. So then I think the last thing I always want you to do for these is plug in what dy dx was. I decided to square the bottom. You don't have to. The numerator, negative x squared, stays the same. All right, so then dy dx right here, I'm plugging in 1 over x squared y. And then plus 2xy. So you see one thing, really I think the only main thing you could do on this, there's a couple of ways to simplify. I canceled out the x squareds. So here's probably a better answer. Negative 1 over y plus 2xy and then over x to the fourth y squared. There's more to do, but I like it up to there. B, so I got y equals cotangent 2x. So y prime, derivative negative cosecant squared, I leave the g, because it was chain rule, times 2. So that was derivative of the inside. I'm going to clean that up real quick, just put the 2 in front. And then I'm going to write what this really means. It really means negative 2, and then cosecant of 2x squared. So you could do a product rule. I'm just going to do a power with chain rule here for the second derivative. So I bring the 2 down, I got -4. Keep the inside, and it's to the first power, times the derivative of cosecant of 2x. Now that is, I'm going to put in parentheses, negative cosecant cotangent. But I have to keep the inside. So whatever the inside was, I keep the same, which is 2x. Negative cosecant cotangent of 2x for both those. That g right there stays the same. All right, and then times the derivative of 2x, which is 2. To clean up, the negatives are positive, then 2 times 4 is 8. And then basically just write everything else. Cotangent 2x. Okay, and last one was c, 7 secant x. First derivative, bring the 7 down, derivative of secant x tangent x. Second derivative, product rule. Second derivative is secant squared x plus second derivative of first, 7 secant x tangent x. So then these become the 7 secant cubed x plus the 7, and it doesn't really matter the order, I put the secant first and then tangent squared x. Let's move on to the back page. So number 10, a tangent line equation. So I do the derivative. I get -2, bring that down, cosine, leave the g, times the derivative of 2, derivative of 2x. So that gives me -4 cosine 2x. And to get the slope, I'm doing y, this is y prime of pi over 2. So get the slope at pi over 2. So we plug in pi over 2, and those cancel. So I get -4 cosine of pi. And that's just -1. So I get 4. That's my slope. I didn't plug in pi over 2 to the original. But when you do that, you would have sine of pi, which is 0. And so it's just 0 times the -2, so you get 0. So I get y minus 0, my slope of 4, x minus pi over 2. And since y minus 0 is just y, I got that, and I distribute this 4x, and then it's 4 pi over 2, which is 2 pi. Okay, a few application problems to finish up. So 11, you got the equation there. 20 exponential equation, 1/2 to the t over 140. So a couple questions. First is initial amount of plutonium. Okay, so you plug in initial means when time is 0. So you just put in 0 there. So then it's going to be 20 times 1/2. Well, 0 over 140 is 0. 1/2, anything to the 0 power is 1. So it's 20 times 1, 20 grams. For B, determine the rate. Okay, I think I'm back. I got cut off there for a second. I think it's good. B, rate of change for plutonium. So I'm going to do the derivative rate of change. So bring the 20 down. Then this is an exponential equation, so that's a to the x. A to the u natural log a times u prime. So I write what I have, 1/2 to the t over 140, times natural log of the base, 1/2, times the derivative of u, derivative of this, which is 1 over 140. That's the chain rule part. Again, that's like, it's really t over 140 is really 1 over 140 t, and the derivative of that is 1 over 140. Okay, so then I just plug in 2. And when you do, you plug in 2, you get -0.098. That's grams per day. So try that out, you plug in 2. Okay, part C, this one has actually no calculus really involved here. Determine when there's only 16 grams left. So that's the amount, A of t. So when is the amount 16? So I just plug in 16 on the left side of the equation and we solve. So I would divide by 20 first. You could leave it at 16 over 20. It'll work out either way, but I simplified that to 8 over 10. 1/2 t to the 140. So then you got to do a log. I just choose to do natural log. Don't have to. Oh, I just made it, just so it's not a fraction, I just wrote this as 0.8. Again, you could leave it at 16 over 20 or 8 over 10. Okay, and then over here, so what happens is it brings the t over 140 down, and then I have natural log of 1/2. I just wrote it as 0.5. Solving for t, so I multiply both sides by 140, and then I divide both sides by natural log 0.5. Okay, we put that in our calculator and you get about 45 days. Number 12. This one's really a beautiful problem because it asks you to look at the rate of change of different parts of the rectangle. So this is a related rate, last two related rate questions. So you have a rectangle. I'm just calling that length. This is the width. I went like this for my, let's see, I called it C. You could call it D for diagonal. I call it C because like Pythagorean theorem, C squared. C is the hypotenuse. So the rate of change of the area, so I'm doing part A. Well, you write down the area formula for a rectangle, length times width. You say you need the rate of change, you need the derivative of this. So you do the derivative here. You gotta do product rule. Oh, and we're doing all of these, since they're related rate questions, d dt for all of them. So really a better way to write this part would be dA dt. So then I write first is L, derivative here is dW dt, plus W second, then derivative of L, dL dt. Okay, we plug in what we know. The length is 12. The rate of change of the width is 2, plus the width is 5 at this moment, and the rate of change of the length decreasing, so it's negative 2. So you get 24 minus 10, so 14. This is area, so it's centimeters squared per second. It's a fun one. Part B, you write down perimeter, 2L plus 2W. So I again do d dt to every term. So it's dp dt, the rate of change of the perimeter. Okay, so here, well, I don't need to do product rule. I just need to do the constant multiple rule, bring down the 2, then do the derivative of L, dL dt, plus bring down the 2, dW dt. And again, we have each of those from before, negative 2 for the first one, 2 there, so we actually get 0. Perimeter at that moment, rate of change is 0, not changing. Okay, and finally C. So a rate of change of the length diagonal. Well, the length of the diagonal, I called it C. We have to do Pythagorean theorem. L squared plus W squared equals C squared. And we can do a square root to solve for C. So actually, there's two ways to do this one. I'm going to do it. I showed something on my answer key that works fine. It's a little longer, I think, because you have to do the derivative of square root. You got to change it to a half power. So what I'm going to do, I think we did this a little bit in class, is just leave it as C squared equals L squared plus W squared, and do d dt to all of these. So it'd be 2C dc dt equals 2L dl dt plus 2w dw dt. They all have a 2, so I can divide every term by 2. And then I'm solving for dc dt, the rate of change of the diagonal. My diagonal is my c. So all I need to do, I still need to divide by c. So it's all of this. It's L dl dt plus w dw dt divided by c. And we have all of those but c. And to get c, I just go back to my diagram, and this was, L was 12, this was 5. So to get c, I do Pythagorean theorem. I get radical 169, which is 13. It's also 5, 12, 13, Pythagorean triple. Okay, so when filling it in, run out of room there, so I'll go to a new page. 12, negative 2, plus 5, 2, and then we just solve for the 13. So it's negative 24 plus 10 over 13, which is negative 14 over 13. Last one, 13. Read through it. You got a telescope there, and you got an angle theta. So here's the picture I drew. Telescope has this angle theta down there. And determine the rocket's rate of change at the moment. Changing the rate point on your pad. So it's 6 kilometers away. We don't know h here. So the rocket's going straight up here. We're looking for the rocket's rate of change when the angle is pi over 3. So we actually don't know this hypotenuse, so it's not Pythagorean theorem, but we have an angle, and so we can do a trig equation. So it's tangent of theta equals opposite over adjacent h over 6. Notice h is changing, so we can't say it's a number. So I need to do d dt to both sides. So the derivative of the left is secant squared theta, d theta dt. And then the right side is 1/6 dh dt. Remember that the derivative of, it's really 1/6 h, and that's just 1/6 for the derivative. Okay, so what do we actually know here? We know theta. So secant squared of pi over 3. We know that. D theta dt, they gave that to us, 0.9. And then 1/6. Okay, and then we're solving for dh dt. So I need to multiply both sides by 6, and then evaluate this, and I get 21.6. And that was kilometers a minute. If you want to, this one, you could do cosine pi over 3, and you get 1/2. And then secant is a reciprocal, so it's 2, and then you got to square it, so it's really 4. So when you plug it in, 21.6. All right, this is Mr. Hunt going over the review. Thanks for watching.